If you studied advanced mechanics, you probably think that the Newtonian, Lagrangian, and Hamiltonian mechanics are all equivalent. And you probably think that because you have been told, and that's what is written in books. For example, the most general formulation is the principle of least action, which would mean that everything that you do in Newtonian mechanics, you can do it with the principle of least action. Or Lagrangian and Newtonian formulation of mechanics are equivalent. And nothing new is added to the physics, we simply gain another more powerful method of working with the physical principle. Or there is no new information on new areas of validity, we'll simply restate Newtonian mechanics in another form. Or, like the Lagrangian version, Hamiltonian mechanics is equivalent to Newtonian mechanics, but is considerably more flexible in its choice of coordinate. And the problem is that this is not true. There are some systems that we can study in Newtonian mechanics that we can't study in Hamiltonian mechanics, and there are some systems that we study in Hamiltonian mechanics that we can't study in Newtonian mechanics. But you shouldn't take my word for it, and because otherwise you would be making the same mistake by just taking the word of what's written in a textbook. So let's go through this very carefully, and then you can decide by yourself who you think is correct. Okay, so what does it mean for formulations to be equivalent? Well, for me, it means that two formulations are equivalent if any system that can be described in one can be described in the other, and vice versa. So, for example, suppose that we have Newtonian mechanics and Hamiltonian mechanics, then we must be able to take any state in Newtonian mechanics and map it to a state in Hamiltonian mechanics. And any possible version of the equation of motion for every combination of the forces, we must be able to find the corresponding equation in the Hamiltonian system, so that we can go back and forth and study it using F equals ma, or studying using it Hamiltonian's equation. So that's, to me, what it means for things to be equivalent. And so that's what we are going to do. So first, let's go and refresh what these formulations are. In Newtonian mechanics, the state is given by position and velocity, and the dynamics, how the system is going to evolve, is given in terms of the forces that are a function of position, velocity, and time. And the law of evolution is given by Newton's second law, which tells us that the force is equal the derivative in time of the mass times the velocity. And here a little bit of notation, this is just the total derivative in time, so it would be d by dt. We just write it like this because it's a lot more compact and allows us to fit more things in a single screen. So that was Newtonian mechanics. For Lagrangian mechanics, the state is the same thing. It's given by position and velocity. And this time, the dynamics, how the system evolves, is given by a Lagrangian. A Lagrangian is a function of position, velocity, and time. There is a requirement, though, to be able to have unique solutions. We must have that the Hessian of the Lagrangian, that is the derivative in the sort of the matrix made by the twice derivative of the velocities, the determinant of this must be different than zero. Otherwise, if you don't have this, you wouldn't have a unique solution. For example, if you just put Lagrangian equals 0, the action for all the paths is all 0, and so you really don't have a minimum, and therefore you don't have a unique solution. This guarantees that you're going to have a unique solution. And the law of evolution is given by the Euler-Lagrange equation, which tells us that the partial derivative in position of the Lagrangian is equals the total derivative in time of the partial derivative in respect to the velocity of the Lagrangian. And again, this is a more complex notation. This would be just partial L, partial xi. It's like this. It's a little bit more compact, and we can go through the math a little bit more quickly. Oh, and you can always stop if you have problem with reading the notation. You can pause the video and look at it more carefully. For Hamiltonian mechanics, instead, the state is given by position and momentum. And here, position, we use the symbol q instead of x, because when you take the partial derivative with respect to this position, here you're taking at v constant, and here you're taking a p constant. So if you use the same symbol, it would seem that those operations are actually the same, but they're not. They're actually different. And so to avoid confusion, I always write Lagrangian mechanics with the x for position and Hamiltonian mechanics with q for position, and it makes the calculation so much easier. So that's what I'm doing here. The dynamics is given by the Hamiltonian, which is a function of position, momentum, and time. And the laws of evolution are given by Hamilton's equation. The total derivative in time of position is given by the partial derivative of the Hamiltonian with respect of momentum. And the derivative in time of momentum is equal to minus the partial derivative of the Hamiltonian with respect to position. And now what we want to go and do is essentially fill in this Venn diagram. So these are Newtonian systems, a Lagrangian system, and a Hamiltonian system. So a system here would be Newtonian, but not Lagrangian and Hamiltonian. So it would only be describable by this formulation, but not the other. And in principle, what we're told is that they're equivalent. So all systems should be here. Every system that is Lagrangian is also Newtonian and also Hamiltonian. So let's see if that's the case. So we're starting with the simplest idea. Let's look at whether there are Newtonian systems that are only Newtonian and not Lagrangian and Hamiltonian. So how do you define the evolution in these three cases? Well, for example, for a single particle in three-dimensional space, the Newtonian system is characterized by three independently chosen functions, the forces of position and velocity, fx, fy, and fz. For the Hamiltonian instead, you have a single function that is the Hamiltonian, which is a function of position and momentum, and the Lagrangian in mechanics is defined by a Lagrangian, which is also a single function of position and velocity this time. Now, what is going to happen is that if we make small changes of the force, the equation is going to have a small variation. In the same way, if we make the Hamiltonian a little bit different, then the equation is going to change slightly, and so is the Lagrangian. Therefore, if we have the same equation that is expressible by all three things, we are going to expect that whatever map we are going to have from the forces to the Hamiltonian and from the Hamiltonian to Lagrangian has to be at least continuous. And here is the problem, is that there is no continuous one-to-one map between the space of a single function, for example, the one for the Hamiltonian and for the Lagrangian, to a space of multiple functions. So already this tells us that Newtonian mechanics has more systems than Hamiltonian and Lagrangian mechanics, therefore not all Newtonian systems are Lagrangian or Hamiltonian. And if you studied advanced mechanics in detail, you know, for example, that when you have dissipative system in Lagrangian mechanics, you can't just characterize them with a Lagrangian, you have to use the Rayleigh potential. And that is already telling you that, well, there are some cases in which you can't just apply straight Lagrangian mechanics. And this is the case. In general, not all Newtonian systems are Lagrangian or Hamiltonian, therefore we have something here. So some system that is Newtonian, but it's not Lagrangian or Hamiltonian. Okay, now let's look at Lagrangian system. Are there systems that are Lagrangian but not Newtonian? And again, we have to map a Lagrangian state to a Newtonian state, which in this case is very easy because they're both position and velocity, so we can always map them. And now we need to check whether we can actually map the equation of motion, so that we can map the Euler-Lagrange equation to F equals ma. And of course we can only do in one direction because we already said that there are more cases for the forces than the Lagrangian. So basically we are just asking whether we can express from the Lagrangian, for the Euler-Lagrange equation, the acceleration in terms of position and velocity. If we can express the acceleration in terms of position and velocity, then we can multiply by the mass and find the force, and therefore we would have the Newtonian equation of motion. Okay, so what do? We take this equation, and they're here. Now we have a total derivative of the partial derivative of the Lagrangian. Well, this is just a function of position and velocity, and so we can apply the chain rule. We first do the partial derivative with respect to x, and then we multiply by dx dt, and then we make the partial derivative with respect to v and multiply by dv dt. Right? This is just the chain rule. And again, if you're not used to this notation, you have maybe to pause and convince yourself, but that's exactly what this is doing. This is just doing a chain rule. And now we have dt, dx dt, and this is just the velocity, and here we have dv dt, which is just the acceleration. So we have the acceleration, we have the velocity. The only thing that we need to do is make this explicit. So we take this and bring it on the other side, and we have that this Hessian of a Lagrangian with respect to the velocity is multiplied by the acceleration is equal partial x of the Lagrangian minus partial x partial v of the Lagrangian times the velocity. And now we need to make the A explicit, and this here, this is just a matrix. So the only thing that we need to do is to take this and invert the matrix. And of course, to be able to invert the matrix, then the matrix has to be invertible. But as you remember before, we said that the determinant of this matrix has to be different than 0 so that we have a unique solution for the Lagrangian. And lo and behold, this is exactly the condition that we need to invert this matrix. And so essentially what that condition for the unique solution is telling us is that we can actually find the acceleration as a function of position and velocity. It's exactly that condition. And so all the Lagrangian systems that give us a single solution are Newtonian systems. So there is nothing here. All the Lagrangian systems are inside here. They're also Newtonian systems. And now we need to understand whether we can have Lagrangian, there are systems that are Newtonian but not Hamiltonian, or all the Lagrangian systems are both Newtonian and Hamiltonian. This is what we need to figure out. Now we have to go then, we have to try to understand how we can map a Lagrangian system to a Newtonian system, and we have the first problem. The Lagrangian state is in terms of position and velocity, while the Hamiltonian state is in terms of position and momentum. And now, this is not trivial, we have to make sure that we can do it. Well, the first part of Hamilton's equation tells us that dtq, so the velocity, is equal to the partial derivative with respect to the momentum of the Hamiltonian. And so what we need, this is essentially a function of position and momentum. So we have the velocity expressed as a function of position and momentum. We need to be able to invert that. We need to be able to say that momentum is a function of position and velocity. And this is general, is not going to be the case. What we want is for this to be invertible and to be differentiable, and therefore the condition is simply that the partial derivative of this function with respect to p, the determinant of that is different than 0. Right? So if we have a function that it's always monotonic, that doesn't have any saddle point, then we're going to have a differentiable and invertible function. And so this basically conceptually, this piece of math is assuming what we call kinematic equivalence. So the idea that the kinematic of the system is sufficient to reconstruct its dynamics and vice versa. So given the position and velocity, we can reconstruct the momentum. And we can do that assuming that the Hessian of the Hamiltonian with respect to momentum is different than 0. The determinant of the Hessian, of course. Okay, so what does this condition map to in terms of the Lagrangian? Well, so this is the condition, this is the determinant. The partial derivative of Hamiltonian with respect to momentum we saw here is the velocity. And the determinant here is going to be equal to the inverse of the inverse metric. And the inverse of the Jacobian is simply doing the Jacobian of the inverse relationship. So the partial v partial p becomes partial p partial b. And from the Lagrangian, we know that the momentum is equal to the partial derivative of the Lagrangian with respect to the velocity. So this becomes a partial v of L, which becomes the Hessian. So this condition saying that the determinant of this matrix is different than 0 is saying that the determinant of this matrix is different than 0. But again, this was the requirement for having the unique solution. So we are guaranteed that for all Lagrangian system that we can go and write Hamiltonian for, this is actually satisfied. And so all Lagrangian systems are Hamiltonian. There is nothing here. All Lagrangian systems are Hamiltonian systems and are also Newtonian systems. Okay, so now the last thing that we need to figure out is the relationship between Hamiltonian system and Newtonian system. Again, we have to map the state, so position and momentum to position and velocity. And we saw that before, how to do it, and then we also need to map the equation of state. Okay, so the condition to be able to map QP to XV is the same as before, is that the Hessian of the Hamiltonian with respect to momentum is different than zero, which is the same condition that we're needing to map between Hamiltonian and Lagrangian. And note that this invertibility is not a requirement of a Hamiltonian. We can have a system that does not satisfy this, and yet we still have something that works in the Hamiltonian system. We will see an example later, but just trivially, you can imagine of setting the Hamiltonian 0. And this will just say that the position doesn't change and the momentum doesn't change. So you have a perfectly a good system that gives you perfect solutions and everything remains the same. And then, of course, you can't go from the velocity to the momentum because the velocity is going to be 0 for everything. So you can't make a one-to-one map. So result of all of this is that not all Hamiltonian systems are Newtonian. Therefore, there is something here. There is something here, some Hamiltonian system are not going to be Newtonian. If they're not Newtonian, they can't be Lagrangian because all Lagrangian systems are Newtonian. Okay, now we have seen what we need for mapping the state. Now what do we need to map the equation? Again, what we really need to show is whether we can write the acceleration as a function of position and velocity. And so what we do, well, the acceleration is the derivative in time of the velocity. The velocity is the derivative in time of position. And the derivative in time of position through Hamilton's equation, we know that it's the partial derivative of the Hamiltonian with respect to momentum. Again, we have a total derivative here. We just do a chain rule. A chain rule, so we do a partial q of this function multiplied by the total derivative of q in time. And then the partial derivative with respect to momentum times the total derivative of momentum in time. Again, this is just doing a chain rule. And now we can expand the dt dq using Hamilton's equation, which is going to be partial p partial h. And we can expand dt of p. And that's going to be partial minus partial q of h. Okay, so this here is a function of position and momentum. So the only thing that we need to do is to be able to write this function of position and momentum in terms of position and velocity. But we already needed to write the momentum in terms of the velocity here, right, under the condition that the Hessian of the Hamiltonian with respect to momentum is equal to 0. So already in that case, and that case is exactly when Hamiltonian system can also be expressed as Lagrangian. So essentially there is nothing here that it's Hamiltonian, Newtonian, but not Lagrangian, because all the Hamiltonian system that can be expressed as Newtonian system have to satisfy the kinematic equivalent. We must be able to write the p as a function of v, and those are exactly the system for which we can go and write a Lagrangian. So this is what it comes to, and this is a little bit weird to look at. But first, before looking at the final diagram, let's go and look at another example of a Hamiltonian system that is not Lagrangian and Newtonian. As a simple example, we can use the photon as a particle. So we know that the Hamiltonian, the energy of a photon is h bar times the angular frequency. The angular frequency can be written as the wave number times c, but then h bar wave number is the momentum. So we have that the energy, the Hamiltonian, as is c times the absolute value of the momentum. So now we can go and apply Hamilton's equation. The partial derivative of the momentum with respect to h is simply c pi over the modulus of p. And the partial derivative of Hamiltonian respective position is 0 because the Hamiltonian does not depend on position. So these are the equation. And here is how it looks. This would be the Hamiltonian as a function of momentum. It's just a line, the absolute value, right, with C as the slope. And what this is going to tell us is that the momentum, like if the momentum is positive, then the velocity is c, and if the momentum is negative, then the velocity is minus c. And if the momentum is 0, this is not well defined. So in fact, this function here would not be differentiable at h equals 0. So the system is not valid. It's not really a Hamiltonian system for h equals 0. And the momentum never changes. So if we have the phase diagram, for any point that we have, any point that it's above, so that it's for p positive is just going to go at equal speed to the right, and instead if you're down, it's going to go to the left, and these points are not well defined. So you see, you can have a system that is Hamiltonian, but it's not Newtonian, not Lagrangian. It's probably not a very interesting system. We can't really do much with it, but it exists. So saying that everything is equivalent is not correct. Okay, so this is essentially the correct graph, the correct diagram. There are Newtonian system and there are Hamiltonian system, and the Lagrangian system are exactly the intersection between Hamiltonian system and the Newtonian system. Conceptually, what happens is that Newtonian system are those for which just by looking at the trajectory, you can reconstruct the momentum, the energy, and so on. There for which the system for which the kinematic equivalence assumption is valid. Looking at the kinematics or looking at the dynamics is the same. You can go and reconstruct one from the other. Hamiltonian systems instead are the ones that are deterministic and reversible. They are the ones that conserve energy. They are the ones that conserve entropy. And the Lagrangian system are exactly those systems that for which both kinematic equivalence and deterministic and reversibility works. So that this is essentially how it works. So I hope this was interesting to you. If you want to look more at the detail of this, you can find more detail in our open access book on the assumptions of physics, which is our bigger research project in which we go and look at all these details. We try to reconstruct the assumption for the pieces of classical mechanics, quantum mechanics, thermodynamics, and so on. And if you're interested in this type of things, like, subscribe, leave a comments, and so on.